In this series of videos, we'll be discussing how to program STM32 microcontrollers in C with various digital signal processing algorithms for audio, and in particular guitar. We've looked at the hardware platform in previous videos, how to program the low-level firmware for the STM32 microcontroller, and various digital effects, for example tremolo, filters, and so forth. So let's take a quick look at the hardware we're using to test and then play through this noise gate effect. Down here, as usual, we have the guitar DSP already running. I've probed it up with some probes, input and output, also with a wave generator at the signal input. I'm using an ST-Link V2 for debugging and programming, and these probes then hooking up to the Digilent Analog Discovery Pro. One is probing the input to this effects unit and one is probing the output, and I also have one of these wave gen outputs connected up to my input, so I can do some bow plots and so forth. This system is then powered via this very simple 9-volt guitar power supply, and that's pretty much it. For recording and then playing through with the guitar, I'll be using my Avid 11 rack, so I can record this straight to the computer. Thank you very much to JLCPCB for sponsoring this video. The guitar DSP PCB you see in this series of DSP videos with STM32 were manufactured and assembled by JLCPCB. If you'd like to get a similar DSP module made for yourself, you can go to my GitHub profile at github.com/PMS67, navigate to repositories, and look for the LDSP audio system on module. Thank you also very much to Altium for sponsoring this video. The LDSP module and a lot of my other work is made in Altium, and if you'd like to try an Altium design out for yourself, you can go to altium.com/YT/PhilsLab to sign up for an Altium Designer free trial. Again, the LDSP audio system on module contains all the Altium design files and manufacturing files for Altium Designer, as well as JLCPCB. On that note, I'd also like to recommend this video on my channel called Mixed Signal Hardware Design Overview, which goes through the basic elements of designing one of these audio mixed signal PCBs with Altium Designer. In this video, we'll be looking at the noise gate digital effects and how to program one yourself on an STM32 based microcontroller. The noise gate is the first non-linear effect that we'll be looking at. In essence, this effect aims to reduce noise in an audio signal that cannot be filtered out easily by other means, for example by low-pass filtering or band-pass filtering. In essence, a noise gate controls the volume of the audio signal. Let's assume we have this audio signal coming at the input here. We define some sort of threshold, which is shown by this dark dashed line, and if this audio signal is below this threshold, we simply reduce the volume to 0, and if the audio signal magnitude is above the threshold, we keep that signal. You can see the corresponding output signal of this very simple noise gate down here, y of n. So anything that is below this threshold line just gets cut out, and anything that is above gets kept. The thing is, we can see later that we can improve on this quite heavily because these sharp transitions lead to rather nasty distortion. The basic logic function of this noise gate is symbolized here, but it's essentially what we talked about. The noise gate, or the very basic form of a noise gate, can be represented by this block diagram over here. We have our input signal, which is sampled at a fixed sampling rate, and we have the noise gate output, which we typically designate as y of n. In between, we have this gain computer, which is centrally configured via the threshold, and if the magnitude of the input is less than the threshold, the gain is 0, otherwise the gain is 1. This gain is then fed into a mixer and multiplied with the input signal. I've already hinted at that this basic noise gate has some very severe problems. You can see here, if we have this arbitrary input signal and we have this threshold set with this line over here, we can see that green means the noise gate is off, red means the noise gate is on as soon as the signal falls below a certain threshold. The problem arises if this amplitude is continuously close to this threshold, so it keeps going above and over and under, or simply goes below the threshold briefly. What happens then is that the signal gets completely cut out. We have basically 0 at the output, and that doesn't really sound great, as we'll see later. It's a heavily distorted waveform, we get additional harmonics, and this isn't great. And here we just have this represented again as the input, and here's the corresponding output. I'd recommend looking at the first few videos in this series of digital audio processing with STM32, in particular this introduction and filters, to get you up to speed if you haven't been following along. A lot of the code is described here, also how to set up the codec, how to set up the STM32F4 microcontroller, so we can actually stream data to and from the codec. Without further ado, let's go over to STM32Cube IDE I'm going to assume you're familiar with the base code, and we'll just go through the few additions we're doing for this noise gate. Starting off, we're going to start off with this very, very basic noise gate. So if the signal, or the absolute value of the signal, is below the threshold, we just cut it off completely. The way we do that is in this very simple case. I haven't done anything fancy, so I've just done a noise gate threshold, which is volatile because we can change it on the fly using one of the potentiometers. And when we process our data, that is, we loop through our buffer, we will get our left input sample, because we're working in mono for this guitar signal, and then we compute the new output sample here. So essentially we take the absolute value of the input and check if that's under the noise gate threshold. If it is, this signal is considered noise, and we simply set the output sample to be 0. Otherwise, we assume the signal is wanted and not noise, and we just set the output sample to be equal to the input sample. So very, very simple noise gate. Now I've already uploaded this code to the STM32, so we can move over to the Waveforms software by Digilent. In the Waveforms software, first of all, to check out this noise gate, we'll be using the WaveGen to generate some sort of test signal at the input, and we'll be reviewing the input signal and the output signal with this scope. On the WaveGen, I've generated a pretty slow 100 Hz, 1 volt peak sine wave, and let's see what the output looks like. Remember, the noise gate threshold is variable with the potentiometer, so we'll see what the different settings look like. So let's go over to the scope, and you can see my channel 1 is my input, which is this yellow trace over here, and channel 2 is my output, both set on the same scale division. Currently, my noise gate threshold is at 0, so I've got my potentiometer completely counterclockwise, so let me just increase that and see how this waveform changes. So now I've moved it almost halfway, and you can see these rather nasty effects of this noise gate. So it is doing what it's supposed to be doing for this very simple noise gate. Then we just change the time base, we can zoom in a bit, and as you can see, it is doing exactly what it's supposed to be doing. So below a certain value, so the threshold seems to be around here, so maybe about half a volt, a bit higher, 600 millivolts, it completely shuts out any of this signal, and as soon as the signal goes above this threshold, which is plus or minus 600 millivolts in this case, we let the signal pass. Now you can see here there's also some time delay because of the processing. So I can increase this even further, and here we then let only, very small amounts, and the magnitude of the signal has to be very, very high for this noise gate to pass anything. So a very simple noise gate seems to be working. Now let's try and listen to that with some audio and see that this doesn't sound very nice. The solution to all this is rather simple, and it's simply to smooth the gain. So instead of having this sort of step between 1 and 0, we can have values in between depending on if we are engaging with a noise gate or disengaging. Gain smoothing is used to prevent heavy distortion of the waveform when the input crosses the threshold value. This means our noise gate can't just have our threshold value as a parameter anymore, and we need 3 extra parameters. Now this depends on the noise gate implementation, you might have more or less. And these extra parameters are part of the gain computer we saw in the block diagram earlier. Most simply, we have 3 times. One is the hold time, and this is the time taken after the input signal crosses the threshold in either direction, but usually it's just in attack mode, that is rather before the noise gate activates. Then once we've passed this hold time, we've passed the threshold, we have this attack time, and this is how quickly the noise gate engages after waiting for a hold time. Attack means our gain falls to 0, which means we are reducing our input signal also to 0. On the other hand, we have our release time, and this is how quickly the noise gate disengages after our input magnitude rises above the threshold, which means our gain increases to 1. So attack means gain falls to 0, and release means gain increases to 1. This might seem a bit confusing to start with, so let's look at an example. Here we have an input waveform, arbitrarily of course, and we have a certain threshold. You can see H denotes the hold time, R denotes the release time, and A denotes the attack time. This is the plot of the input waveform, and this is the plot of the gain. So let's start over here. We are below the threshold, the noise gate is engaged. Once we pass the threshold, we want to let the signal through again. We wait a tiny amount, and this depends on implementation. Most people don't have the hold time implementation as part of the release. We wait a certain time where the gain stays at the whatever value it was before, and only afterwards the gain slowly ramps back up, or rather exponentially, back to the gain of 1. And this coefficient of how quickly this exponential ramps up is our release time coefficient. Then our gain is at 1 because the magnitude of the signal is above the threshold. But then here again, we cross down below the threshold, we wait a bit during our hold time, and then we start attacking. So during this hold time, our gain again stays constant, and afterwards we roll off the gain exponentially. You can already see here, release and attack times can and usually are set differently. Usually the attack time is much slower than the release time. The hold time implementation is rather simple. We wait for the threshold crossing of the input signal, and if the threshold is crossed in either direction, we essentially just start a counter. So you can either do this for release, or for attack, or for both, but typically it's only done for attack. The attack time implementation is rather simple as well. We assume a static gain of 1, which means the noise gate is disengaged. We multiply our input signal by the static gain, which means all of the input signals at the output. Now, after we cross this threshold, so for example here in the attack time, as you can see on this graph down below, we are crossing from above, so we're going from this region down below the threshold. Then we wait until the hold time counter from before exceeds the hold time, and then we set the static gain to 0. So we're jumping from 1 to 0, and the noise gate is now engaging. We're not multiplying the input signal by the static gain anymore, because that would of course introduce distortion. We apply a first order low pass filter to the static gain to get the smooth gain. And that's really that simple. So instead of using a static gain, 1 and 0 only, we simply apply a first order low pass filter every time we attack and every time we release. A filter can look as simple as this. So where the output of the filters are smooth gain, and the input is the static gain. And we have this coefficient alpha, which is a value between 0 and 1. This is a simple first order digital low pass filter, which we've seen many times on the channel before. The filter response is exponential, and our alpha sets the attack time constant. For the release time, we have something very similar, except we are now flipping the static gain from 0 to 1. And the similar gain smoothing filter for the release time as well, and we'll see that in the STM32 CubeIDE implementation. Here are some implementation points we need to consider. The low pass filter is the same for both release and attack time. However, the coefficient changes depending on if we're attacking or if we're releasing. So the smooth gain is the same output for both release and attack time, but we use different coefficients. During the hold time, the smooth gain does not change, and the release, attack, and hold times can and usually are different, and usually they're given in milliseconds. So let's go over to STM32 CubeIDE to now implement this noise gate and look at the difference between the simple and the more advanced noise gate. What we saw from the slides, you can also see very nicely on the MathWorks website, the guys that make MATLAB, and they have this noise gate or dynamic range gate as they call it, and this describes the function very nicely. It also describes the different elements in this algorithm, for example, the gain computer, gain smoothing, and so forth, even though they do use the approach where they do everything in decibels, then convert to linear, whereas we're just converting to linear. They also reference this paper on digital dynamic range compressors, so noise gates are very closely related to limiters and compressors. I think this is a very interesting read if you are into these kind of things, and I'll leave a link to this in the description below. This paper seems to be freely accessible by the Queen Mary University of London website. In STM32 CubeIDE, you can see I've written this quite a while ago. Here I have my GDSP noise gate. Essentially, as usual, I will have some sort of struct to hold various filter or algorithm parameters, for example, the threshold, the hold time in seconds, attack and release coefficients, and so forth. I have an initialization function where I take in the noise gate struct, the threshold, attack time, release time, the hold time, and the sample rate at which my algorithm will be running. And I have this update function, which essentially performs the main work of this algorithm and returns the output of the noise gate. And I've got these various functions which set the threshold, as well as the attack and release time. So basically they can recompute these attack and release coefficients. So let's go through these functions one by one. Let's start off with this initialization function, which essentially converts the hold time in milliseconds to hold time in seconds, just dividing by 1000. We also set a threshold, which is a different function. We compute the attack and release time. We store the sample times and reset our counters as well as our smooth gain. Before we go to the update function, let's look at the threshold and attack and release time. Threshold essentially just checks if the threshold is in a meaningful range, so that is between 0 and 1, and then sets the threshold. The attack and release time functions essentially compute, given an attack time and a release time in milliseconds, the required filter coefficient for our first order low pass filter, and using these formulae over here. Remember, the response of a first order low pass filter is exponential, and we can use approximately the time constant of 2.2 RC or 2.2 tau as our time constant, and this is where this formula comes from. This order of magnitude of 1000 is because we're doing everything in milliseconds. Then going to our actual noise gate update function, we pass the noise gate struct as well as the input to our noise gate. The first thing we need to do, of course, is take or get the magnitude of the input, using this fabs function, which is part of the mathlh library. Of course, there's more efficient ways of doing it, but this works completely fine. We initially assume a gain of 1, that is, if the absolute input is greater than the threshold, but then we check if the input absolute is less than the threshold, and that means we have to reduce our static gain to 0. So the input is below the noise gate threshold, and thus the gain is 0 because we don't want to let any signal pass. But remember, we are doing smooth gain now rather than just this static gain calculation. So we need to pass this on from our gain computer, so to speak, to our smoothing function where we use our low-pass filters. For gain smoothing, as we saw before, we have these attack and release stages. Attack means we are decreasing our gain, the noise gate is engaging, the noise gate is attacking. So if our gain is less than the smooth gain we want to attack, so if our gain computer tells us, okay, we're jumping from a gain of 1 to a gain of 0, for example, we want to attack. In the attack stage, we need to wait this certain hold time. Remember, you can either have the hold time both in the attack and release stages. For this implementation, I have just used the attack stage for the hold time as well. So we have this attack counter which counts up if we are in an attack stage and checks if we are larger than the hold time we specified. If this is the case, we attack, which means we decrease the gain by using our low-pass filter with the attack coefficient, and this is important. So our input is our static gain, and our feedback is essentially our smooth gain. Now, in the case that we haven't reached the hold time yet, we do not smooth the gain, we just increment our counter, essentially just waiting until we can smooth the gain. So remember, this was our attack stage, and we also have to do something fairly similar in our release stage. So once the signal passes above the threshold and our gain goes back to 1, we're letting signal pass, we want to return back the gain to 1, not immediately, but smooth it up. And typically this release coefficient or the release time is much shorter, maybe 1/10 of the time shorter than this attack time. But we use a similar formula. The smooth gain, again, is the variable being worked on, except we're using the release coefficient in this case. Also, when we're in the release stage, we're not attacking anymore, and this is a good time for us to reset our attack counter. All the noise gate then needs to return is essentially the output of the noise gate, which is the input to the noise gate times the smooth gain. And that's pretty much all there is to this noise gate, so pretty simple algorithm. Now there's quite a few things you need to tune, that is the attack time, the hold time, the release time, the thresholds, and so on. But nicely enough, we can map most of these to different potentiometer values. So if I go to my main.c, you can see I've included my noise gate, and in my processing function, I simply call noise gate update, passing my noise gate struct, my left input, and then I pass that straight to the output. Up here, you can see I've defined the noise gate struct as a global entity. In my main function, I simply initialize this noise gate to fairly sensible values and pass it also the sample rate. I also have my control settings, which I change on the fly. So every time I adjust a potentiometer, plus or minus 1 or 5%, in this case, I've set it to 1%, so we don't get too much jitter. I can change, for example, the attack and release time between about 1 and 100 milliseconds. And I'm setting the release time here as 1/10 of the attack time, just to show you that it should be typically quite a bit shorter than the attack time. On my other potentiometer, I'm changing the hold time of my noise gate. And my last potentiometer, I'm afraid I only have 3 here, so I'm setting the threshold. So I can vary the attack and release time with one potentiometer, I can vary the hold time, and I can vary the threshold. So this would be pretty interesting to look at. I've already uploaded this code to the GDSP system, so now we can move over to Waveforms to see what this does. In Waveforms, you've seen this before, this time I'm passing as an input, which is the yellow trace, a triangle wave. Doesn't really matter, I could have done a sine as well, but I thought why not mix it up. And you can see the blue is my output trace. Now I've set a certain attack time, I've set a certain release time, and I've set a certain threshold. Annoyingly, there's a bit of a time delay or phase shift in here, which means these traces aren't exactly overlaid. I've set a certain threshold, which seems to be, around midway of this input wave. So below that, our noise gate essentially clamps, and we get 0 at the output. Then you can see this fast exponential over here is our release filter working. So this is 10 times faster than our attack filter. So we're releasing very quickly, so as soon as the input signal goes over the threshold again, we can go back and pass this signal very quickly. So we get the peak of our triangle wave at the output over here. So as the input goes down, we can see this in the blue output trace over here. And once it reaches this threshold value again, we have a slower attack low-pass filter working. So you can see this exponential decay is much slower than this release exponential increase over here. So we have different orders of magnitude in the low-pass filters when we smooth the gain. So here's the attack stage, and here's the release stage. And then we just clamp it down to 0. So you can see there's far less sharp transitions if we compare that to the very simple noise gate. Here we have an exponential increase in the release stage and an exponential decrease in the attack stage. So this should give us a better sounding noise gate. We'll have less harmonics and less distortion. I can also play around with my threshold, for example. So if I move my threshold around, you can see I'm letting more of this triangle wave pass. So let me play around with the hold time and pay special attention to where we are attacking. And remember, the hold time changes the time before the noise gate engages. So decreasing my hold time makes my system attack faster, and increasing my hold time makes my system respond slower. I can also change the attack and release times or coefficients, which means you'll see difference in these exponential changes over here for the release and on the right side here for the attack. So now I've increased my release and attack times. You can see I have a much slower exponential increase and a much slower exponential decrease over here. So this looks like it's working. Let's see how this sounds with the guitar plugged in.